Today we're diving deep into a really fascinating area of modern geometry called orbifolds. And, well, the name itself has a pretty fun origin story.
Oh, it does. The term orbifold, it's short for orbit manifold, came from William Thurston back in the 70s. Apparently, it wasn't some high-minded committee decision.
No.
No, the story goes it was actually chosen by a student vote. Beat out things like foldamani, if you can believe it.
Foldamani. Okay, orbifold sounds a bit more dignified, maybe.
Yeah.
So orbit manifold. Does that name tell us what's going on?
It gives you a good hint. Basically, an orbifold is a step beyond a standard manifold. You know, a manifold is locally smooth, looks like flat Euclidean space up close.
Right.
While an orbifold is locally modeled on a quotient of Euclidean space. Think of taking that smooth space and folding it or dividing it out by some kind of symmetry, specifically a finite group action.
Oh, okay. So these were actually studied before Thurston gave them that catchy name.
Yes, that's right. Back in the 50s, Ichiro Sataka called them V-manifolds. They're fundamentally the topological space you get underneath a discrete group action.
So our mission today, really, is to figure out why we need these generalized spaces. You know, what's the point of studying these folded or quotiented geometries? And where does it lead? Apparently everywhere from cosmology to music.
Exactly. It's about understanding what crucial information the orbifold structure captures that, well, a simpler viewpoint misses.
So what is that extra information? If you take a quotient, sometimes the underlying shape doesn't even change, topologically speaking.
That's the key point. The orbifold structure isn't just about the final shape, the quotient space itself. Critically, it encodes the structure of the isotropy subgroups.
Isotropy subgroups, what are those, practically speaking?
They're the points that stay fixed under the symmetry operations. Think of them as the singular points, the places where the folding or identification actually happens. A standard topological look might miss these entirely.
So one shape could actually have different orbifold structures layered on top.
Precisely. Take a simple sphere, S2. If you quotient it by a 180-degree rotation around an axis, say the z-axis, topologically, still looks like a sphere. But the orbifold structure is different. It remembers those 2 points, the poles where the rotation didn't move anything. Its orbifold fundamental group becomes Z mod 2, not trivial like the spheres. It tells you there's a twist, a symmetry baked in.
Okay, so it's like seeing the hidden seams or fixed points that the overall shape hides.
Yeah.
That sounds like something that could be useful in physics, maybe, dealing with singularities.
Absolutely. And that brings us straight to string theory. It's a major application.
How so?
Well, string theory operates in 10 dimensions, right? To get down to our everyday 4 dimensions, the extra 6 need to be compactified, curled up really small. Often this is supposed to happen on what's called a Calabi manifold.
Which I gather are quite complicated beasts mathematically.
Extremely. They're hard to work with. Orbifolds offer a way around this sometimes. They can be seen as sort of degenerate or singular versions of Calabi manifolds.
Easier to handle.
Much easier to calculate with, yes. They let physicists work with spaces that have these controlled singularities, these orbifold points, which often simplifies the models dramatically while still capturing essential physics like supersymmetry.
Okay, from 10-dimensional physics to something completely different. Music theory. How does that connection work?
It's a beautiful application, actually, developed by Dmitry Tomasko. He realized you could model musical chords geometrically using orbifolds.
Chords, like CEG.
Exactly. Consider chords with end notes. First, you identify notes an octave apart. They're treated as the same point on a circle. So end notes live on an n-dimensional torus, like end circles multiplied together.
Yep.
But the order you play the notes in a chord doesn't usually change the chord's name or function, right? CEG is the same triad as EGC. So you need to account for this permutation symmetry.
Ah, so you take the n torus and you quotient by the ways you can reorder the end notes, the symmetric group Sn.
Precisely. The resulting space, TNSN, is an orbifold.
So what does the orbifold for a standard 3-note chord, a triad, look like?
It turns out to be topologically like a triangular prism, but with a kind of 120-degree twist built in. And when you analyze the geometry of this specific orbifold,
Yes.
you find that points representing major chords and minor chords naturally cluster around certain regions, specifically around the points representing the perfectly symmetrical augmented triads. The geometry actually maps out harmonic relationships.
That's genuinely amazing. We've gone from abstract topology, these sort of folded spaces with singular points, all the way to the underlying structure of music.
It shows how fundamental these geometric ideas can be, and it leads to a rather provocative thought, I think.
Go on.
Many of these orbifolds, especially those related to non-positive curvature, are what we call developable. They arise from a group acting on some simpler, universal covering space, like unfolding the orbifold back into something simpler. So the thought is, could we apply this idea elsewhere? Could complex, maybe singular-looking structures you find in, say, large data sets or information networks actually be developed? Could we find a simpler underlying generating symmetry or group action if we look at them through this geometric orbifold lens?
Using geometry to find hidden simplicity in complex data. That's definitely something to chew on. A fantastic place to pause.
Indeed.
This deep dive was sponsored by embersilk.com. If you're looking into AI education or integration for your business, Embersilk is the answer. Check them out at embersilk.com.
And a quick reminder from us, if you enjoyed this discussion, please subscribe to the deep dive and consider leaving a 5-star review. It genuinely helps us reach more curious minds.
It really does. Thanks for joining us.